Okay, so last time we were looking at this Dijkstra algorithm for finding shortest path trees. It means you can start from a root node or a source node, and starting from it, you can find the shortest path to every other node in the graph. So that's what is called the shortest path tree. So we looked at one example. We'll go to one more example and then look at the time complexity and other properties and so on. Okay. So the way we do this is, so we are going to find the shortest path. Distance means the weight of a path is the sum of the edge weights. So for starting from the root node, so let us say the root node or starting node, which you can also call the source node, is A in this example. So the distance from the root node to itself is 0. When I say distance, it means the shortest path weight. And then the distance is estimated shortest path weight to the other nodes is infinity, because we don't know what is the shortest path to the other nodes. Now, one important assumption of Dijkstra's algorithm, which we'll make use of later when you look at the properties of the algorithm, is that it requires all the edge weights to be positive. Means all edge weights have to be greater than 0. So no edge weight can be negative in a graph, in order to use Dijkstra algorithm. So that's one requirement of Dijkstra's algorithm. So later, after this, we'll see another algorithm to find shortest path trees on even if a graph has negative edge weights. But Dijkstra's algorithm cannot be used to find shortest path trees if a graph has negative edge weights. So that is something you have to remember. Alright, so we initialize the tree like this. So for the root node to itself, the distance is 0. For everything else is infinity. So what we do is, in each iteration, we pick the minimum among the vertices that are not yet been optimized. So we'll consider the root node also not optimized to begin with, and 0 compared with everything else is infinity. So 0 is smaller. So we remove the root node from the or we say the root node is optimized. So later when you look at the pseudo code, I'll show you how we store this in a data structure and do. So like right now, in each iteration, you pick the node with the smallest value among the nodes that are not yet considered to be optimized. So again, when I say optimize, it means we have found the shortest path from the root node to that node. So to begin with, we have found the shortest path from the root node to itself. Alright, so now we try to relax the neighbors of the node that we just optimized. So in this case it is A, and we have to relax its neighbors. So relaxing the neighbors means by going through that node, can we reduce the estimated path weight to the neighbors. So in this case, if you go through A, it's going to be 0 plus the edge weight phi, and is less than infinity. So phi is less than infinity, so we make the estimated pathway to B as phi and make A as a predecessor, because we are able to reduce it from infinity to phi by going through this edge. So highlight that edge. Similarly, 0 plus 3 is 3 less than infinity, so we can make this 3 and highlight this edge. So that's the first iteration. Now we have 3, 5, infinity, infinity and infinity are the data or the estimated shortest path weights for the nodes that are not yet optimized. So among these numbers, you pick the smallest value, which is 3. So when you pick that 3, it means you have optimized that vertex, the corresponding vertex C. That means you have found the shortest path from the starting node or the root node A to that vertex C. So whatever else you try, you cannot find the shortest path of weight less than 3 from A to C. So that's what I mean by shortest path, or mean by telling the vertex has been optimized. So now try to relax the neighbors of C. So you have B and E as the neighbors of C. So by going through C, can you reduce the estimated shortest path weight to the neighbors? So that's what we're going to see. So 3 plus 1 is 4, less than 5. So we can make this 4 and remove the highlight on this edge and highlight this edge that was used to reduce from 5 to 4. If, for example, if this edge weight is say 4, 3 plus 4 would be 7, and 7 is not less than 5. So in that case, we would stay with what we have. So we can reduce it. We want to only reduce it if possible. We don't want to increase it. So even if there's a tie, so in this case if it's say 2, 3 plus 2 is 5, same as this 5. So we'll stay with whatever we have. So of course you can change the highlight and make this highlight this edge. So it's up to you how you break the tie, doesn't matter. But as a convention we'll just stay with whatever the value weight we have if there's a tie. Alright, so now 3 plus 4 is 7 less than infinity. So we can make this 7 and highlight this edge. So those are the two neighbors of C that we can try. So now, of course, A is also a neighbor of C, but A has been optimized already, so we cannot do anything with that. Alright, so at the end of this iteration, we have 7, 4, infinity, infinity. Those are the four values of the vertices that are not yet optimized, the shortest path estimates. So among these, pick the smallest value, which is 4. So when we pick that 4, it means the corresponding vertex B has been already optimized. So that means we have found the shortest path from A to B of weight 4. So now by going through B, we are trying to see if we can relax the neighbors of B. So D is the only neighbor that has not yet been optimized. So let's try. So in this case it will be 4 plus 7 is 11 less than infinity. So we can make it 11, highlight this edge as a predecessor edge. So that's the only neighbor of B. So we're done with that iteration. So we have 11, 7 and infinity. Among these, 7 is the smaller. So we say the corresponding vertex E has been optimized. So now we again try to relax the neighbors of E, which are D and F. Now we are going to check and reduce the estimated path weight to D by going through E. So we do that by checking up to E is 7, that's the shortest path weight to E, plus the edge weight 2. So 7 plus 2, 9 compared with 11. 9 is less than 11, so we can make this 9. So since we reduced it, we remove the highlight on this edge and make this edge as the predecessor edge. That means you have to go through E to reach D, and based on what we know so far, right? So now again 7 plus 3 is 10 less than infinity, so we can make 10 as the estimated pathway to F and highlight this edge to D, so to E. So now 9 and 10 are the two estimated shortest path weights, so we pick the minimum among them, which is 9. So now try to relax the neighbors of D. So it's going to be F, the only neighbor that is not yet optimized. So 9 plus 6 is 15. 15 is not less than 10. So we want to only reduce it if possible. We don't want to increase it. So since we cannot reduce it, we'll just stay with 10. And that's the only neighbor of D we can try. All other neighbors of D are already optimized. So once we are done with that iteration, F is the only vertex that has not been yet optimized, and it's now optimized because that's the last vertex out there with estimated shortest path weight 10. So now you put together all the highlighted edges, what we get is a shortest path tree starting from the starting source node or root node, whatever you want to call it. So in this case A to everything else. So if you want to reach from A to D, you have to go A, C, E, D. If you're going to go to F, A, C, E, F, and so on. So again, what we are trying to minimize is the sum of the edge weights, which is called the path weight. So the path weight is the sum of the edge weights, and that's what we're going to minimize. Find the shortest path. So shortest path means the path with the minimum weight from the source node. Okay, so that's the shortest path tree. So let us look at the pseudo code of how we do that for Dijkstra's algorithm, and then we look at the time complexity. So we are going to make use of a data structure to store the estimated path weights for the nodes. So we could use a min heap for this. So let us see how we do that really. So here I have given just a pseudo code, and now I have also given you the time complexity. So let us look at this version so that it becomes easy to analyze the time complexity also. So to begin with, we initialize the estimated path weight for every vertex other than the source to infinity, and then for the source it is 0. So this is what we do as part of initialization in this example. Now if you are using a min heap, then it will take v log v time to build the min heap with these values. Now, if you're really programming it, you won't put everything as infinity. So how you do that initialization is assume a very large value and make them very kind of different from each other. So if you say 10,000 as the estimated path weight corresponding to infinity, you make for one node it is 10,000.1, for another node 10,000.2, 10,000.3 and so on. So that way each node has a unique infinity value in the main heap, and you can kind of arrange them in the main heap. Now for the source node it is 0 estimated path weight, so the source node will be the root of the main heap. Again, remember what a main heap is. A main heap means a binary tree where the data for every internal node is less than or equal to the data of the two child nodes. So in this case the root node starting node has the smallest data, so that will be the root of the main heap. Then you maintain a set of vertices, let us call it as S, as a set of vertices that have been optimized as part of the algorithm. So to begin with, that set is an empty set because we have not yet found the shortest path from the source to every other vertex, including the source itself, we have not yet found. And let us call the other set as Q, is a set of vertices for which we know only the estimated path weight from the source. So that set is going to have initially all the vertices in the graph, and that is the queue we call as a priority queue. So the min heap really corresponds to this set Q. So you're going to use the min heap as a priority queue because when you want to now dequeue from the queue, you're going to remove what? The vertex that has the smallest estimated path weight. So it's not a simple queue, it's not a regular FIFO queue, it is a priority queue. Alright, so we now go through a sequence of iterations, and in each iteration we check whether the priority queue has already become empty or not. So to begin with, it's not empty, it has all the vertices in the graph. So we kind of dequeue, so that's what this step means. You take out the node that has the minimum data among the nodes that are out there, and remember that's what we do in each iteration. Among the vertices that are not yet optimized, so the queue is a set of vertices that are not yet optimized, you as I said, dequeue the queue, and that will get you the node with the smallest estimated shortest path weight among the vertices that are not yet optimized. So let us call that vertex that we dequeued from the queue as vertex U. So when I said when you dequeue the queue and you found the pick up the vertex the smallest estimated path weight, that means we have optimized that vertex. So you add that vertex U to the set S, that is a set of vertices that have been optimized. Okay. So it is removed from this queue and added to the set S. So now try to relax the neighbors of S of U. That's what we're trying to do. So for each edge UV attached to U, try to see if you can reduce the path weight to V. And for that, make sure that V, the neighbor, is not yet optimized. So it should be in the set Q, not in the set S. So if it is set in the set Q, and by going through U plus the edge weight from U to V, you can reduce the estimated path weight to V. So if D of V means the distance or the estimated path weight from the source to V is greater than the estimated path weight to U plus the edge weight UV, that's the time you say you can reduce the estimated path weight of V further. So you set estimated path weight of V to be the estimated path weight to U plus the weight of the edge UV, and make the edge as the predecessor edge. So you do that by setting the predecessor of V is U. So that means in order to reach V, you have to go through U. Now remember, we are changing by this way the estimated path weight for a vertex V. So that means the Q, the priority Q, has to be reheapified. So one reheapify operation will take log V time. Use all these things in the data structures class. So you do that for every neighbor that you can relax for this vertex U that you optimized, and that's the iteration. So in each iteration you dequeue a vertex from the queue and relax its neighbors. So if you look at the time complexity of this loop, so in each iteration you dequeue one vertex, and again when you dequeue vertex you have to reheapify the heap to restore the heap property. So that will take log v time. And how many iterations we do? We do, like, of course, we run this until until the queue becomes empty. So that means you're running it for v iterations. But the last iteration we don't really do anything else. So, but as per the pseudocode and the logic, we are running for v iterations. So this step of dequeuing the queue v times will take v times log v time. So that is this v log v time. And this first v log v is to set up the min heap. So that's that v log v. Plus this dequeuing process for v iterations will take v log v time. And now the relaxation process. So if you think about this, what we are doing is like you are dequeuing a vertex and relaxing its neighbor. So in this case, when you dequeue A and optimize A, relaxing neighbors means looking at these two edges. Then you are optimizing this vertex C and looking at its two neighbors means you're looking at these two edges, CB and CE. Then we're looking at this edge from B to D. Essentially, as we go through the iterations, we are basically looking at every edge in the graph. And for each such relaxation step, we may end up changing the estimated path weight to the neighbor. For example, when relax this edge, we are going to reduce estimated path weight of B from 5 to 4. That means we have to reheapify the heap and change the corresponding position for B, right? So we have to reheapify at the worst case as to relax each edge. So across all the iterations, we are basically trying to relax E edges. And for each such relaxation step, you may have to spend log v time to reheapify the heap after you change the path weight. So that will take E log v time. And that's actually the most time consuming step of the algorithm, relaxing each edge across all the iterations put together. We are not relaxing each edge for each iteration. So if you, as I said, for each iteration, you're just relaxing the neighbors of a vertex. But when you put together all the edges that are considered across all the iterations, then we are basically relaxing every edge, all the edges in the graph. So E is the total number of edges that are going through relaxation across all the iterations put together, and E log v time is the time complexity of doing relaxation and trying to change the estimated path weight and reheapify the heap. So if you put together then all this time complexities, it will be like v log v plus E log v. So now between E and V, which is E is the number of edges and V is the number of vertices, we can always say E is more dominating. So you need to have at least V minus 1 edges for a graph. So for the vertices to be reachable to each other. So the number of edges will always be larger than or greater than or equal to the number of vertices. So we can make this term as the dominating term. So the overall time complexity of Dijkstra's algorithm can be considered to be E times log V. Okay, so that is how you come up with the time complexity of Dijkstra's algorithm. So let me stop for a moment and save this video.